Okay, so moving on to questions 66 to 68. In the first, well, you can tell by the fact that they have Bernoulli's equation here that this is going to be a passage about fluid dynamics, whereas before earlier, I think it was around question 30 or something, we looked at fluid statics, which is fluids that are not moving. Now we are looking at fluids that are moving as well. So anyway, in the first paragraph, they talk about the flow rate, the amount passing, and it's equal to AV. And they say this flow rate is constant. I'm not sure why they put that in two different sentences, but they could have just given this to you and said AV is constant. So that's important, and that's called the continuity equation, actually. They don't mention it, but that's a continuity equation, and it means that fluids that are incompressible, moving through pipes or tubes, we can deal with them like this. AV is constant, and you know, in science, whenever you see something is constant, it means A1 V1 is equal to A2 V2, etc. So now we look at the first question. A horizontal tube with diameter that branches into two horizontal tubes, each with a diameter that. The speed. Okay, so if it's we're talking about the diameters of tubes, well, first of all, you know, a tube looks something like this. I'll try to draw a horizontal tube. I guess it changed sizes, but whatever. This is what a tube looks like, and this is not referring to the same area that you think of when you hear pressure is force per unit area. That's area of of a container, of a table, or whatever. That's force per unit area, pressure. This area is not that at all. This is cross-sectional area. So this is a tube. You take a cross-section of that, and it's referring to this. And so the cross-sectional area of a tube is clearly a circle. And the area of a circle is pi r squared. And yes, you are definitely expected to know that. Pi, of course, is approximately 3.14, and so we have r squared with radius. So they're telling us that we're getting half the diameter. We're going from 2d down to a diameter of d. So if you have half the diameter, and diameter is just a line, right? And radius is half of that. So that means that if you have half of the diameter, you're going to have half of the radius. So if you have half of the radius, now we're going back to this equation. If we know that this is supposed to be a constant, right? So, and we know that this is pi r squared. And if we have half of the radius, we're going to end up getting, because it's half of the radius, it's squared, we end up getting pi r squared over 4, because the 2, half of the radius, will be squared, so we have over 4. To keep this constant, what's the velocity going to have to do if this is going to be constant? The velocity has to be 4 times. So this creates 4v. But we have 4v, 4 velocity, that's breaking up into 2 different tubes. So each tube will have twice the velocity because it's 2 different tubes. So for the question 66, the answer would be C. Question 67 and 68. I'm sure you're happy to have the ebook that ACER gives, because in the booklet, the physical booklet that I have, the diagram didn't come out very well, but I can make certain assumptions about what the dam must look like. But nonetheless, 3 possible designs for a new dam are shown. For which design will the water pressure at the base of the dam wall be the greatest? Well, you may have known already the equation for the pressure, but if not, it was given to you that if the liquid is still, and we expect that the liquid is not really moving very much, that pressure plus rho GH is constant, and actually a better way of moving this equation around, because that's constant, a better way to use this equation is to talk about the fact that there is a change in pressure. This is an equation you can use for statics, which is rho g delta h. So when you are in a liquid, okay, and you move from one level to another in the liquid, and you change the depth in which you're in, the change in pressure as you go from one place to another place is equal to rho g delta h. So it's equal to the density of the fluid times gravity times the depth that you go down. Notice it's not dependent on the width of the container, and so also it also shows you that the pressure here, right here, is going to be the same as long as the depth is the same. So those are the important points. So when they ask, will the water pressure at the base, for which design will the water pressure at the base of the dam wall be the greatest? Well, if you look across, the base of the dam wall seems to be at the same depth. So if it's at the same depth, it doesn't matter what the shape is of the dam, because the pressure that it would feel at that depth is dependent on the depth. So the pressure would be the same in all designs. It would be the correct answer, answer 67. Then 68, for which design will the total force of the water on the dam wall be the least? So first of all, force on the dam wall, that doesn't ring any bells for me about, an equation or whatever, but I know that this whole thing has been talking about pressure. And so if I hear the word pressure and I hear the word force, of course I'm going to think about that pressure is force per unit area. And again, this unit area is completely different from this cross-sectional area. This is the area where the actual pressure is on, and that would mean on the dam wall as well, that kind of pressure. So, but this is asking where would the total force be the least. So I'm going to rearrange the equation and put that force is the pressure times the area. Okay, now ACER very nicely had the previous question make us think through the fact that the pressure at any given point or depth is going to be the same. It won't change no matter what the shape of the dam is. So that's point number one. The pressure at any given point won't change. So now let's talk about the area. The area that the dam wall presents is quite different, because for structure one, which goes straight down, the dam wall is a particular size, but for the other structures, though they're going down the same, they're presenting a hypotenuse, aren't they? Because they're at an angle. So the shortest line would be this line. It'd be shorter, I should say, than the hypotenuse. The hypotenuse is the longest line. And so this presents a greater area than this line alone. And for this reason, wherever you have the smallest area, smallest A, when the pressure is the same at that level, at whatever level you're talking about, smallest A means it's going to have the smallest force of water on the dam wall. And so the correct answer for 68 is A.